Very good morning, everyone, and a warm welcome to this webinar series, which Water Digest has exclusively planned and organized for the water industry professionals. As you know, that Water Digest had been doing a series of webinars and a lot of training programs and panel discussions, and this was our one initiative wherein we wanted to keep the industry engaged, and we also want you all to utilize your time fruitfully, constructively in the right direction. So today's topic is one of the most important topics as we all talk about circular economy today, but what it is. Yeah, so we have an expert who will be talking more about circular economy and especially advances in the membrane technology to drive it. So we have the topic, the advances in membrane technology to drive a circular economy. I'm glad that you all have joined us today, and I really look forward to an enriching and informative webinar series and webinar today by Mr. Kulkarni, who is one of our esteemed experts of the segment. He brings along more than 2 decades of experience with him. He's currently with Dupont Water Solutions, again, one of the main organizations known in the water industry. And he will be delivering and talking about innovative solutions of ultrafiltration, RO, nanofiltration, and many more. So I would leave rest of the things for you to explore yourself. And before I hand it over to the trainer, I would like to share the format. So the program will run for almost an hour. For 45 minutes, our trainer will be talking about the key points which he wants to highlight with regards to this particular topic. And post that, we'll be taking up 15 minutes question answer session. In case we miss out to your question or your query, then maybe we'll take it over, we'll certainly take it over email. And for putting up your query and questions, right in front of you, there is a window. There is a chat session, and you may write your question and query, and we'll make sure that your queries are answered. If we can take it up during the webinar, it's good. If not, then we'll answer it over an email. Also, after half an hour or so, whatever being taught throughout the session, so maybe we'll share an interactive and in a polling section, which is right in front of you. We'll share one questionnaire also, and we look forward to your knowledge base, which you have gained during the course of the webinar. Rest, I leave it to Mr. Kulkarni to take it forward. And once again, I welcome all the participants and a very warm welcome to our trainer, Mr. Kulkarni. Over to you, Mr. Kulkarni.
Thank you, Ms. Anupama. Thank you. Good morning to everybody who was able to participate, who is able to attend. Hope everybody is safe and secure in this particular environment, which is slightly sort of disappointing. So today's discussion is about advancements in membrane technology. We are trying to understand that what are the things which could help drive a circular economy. I'm moving to the next slide, which is the slide of agenda. We're trying to cover the trends which are happening in the industrial wastewater market. We're trying to understand what is minimal liquid discharge, or MLD, the short form. We're trying to understand what's going to be the role of Dupont as a technology partner in helping the customers treat their challenging waters. How Dupont is bringing the innovations of reverse osmosis membranes or nanofiltration membranes in terms of maximizing the water recovery, in terms of reducing the salt which is being sent to the landfill. These are some really good innovations which we'll try and present. Also, we'll try and sort of catch up with some of the practical examples, some of the live examples which textile industry especially is throwing up, wherein they are achieving the goal of not only minimal liquid discharge, but zero liquid discharge. And this is what we call as a circular economy. A circular economy wherein we are trying to maximize the recovery of wastewater. We are trying to basically reduce the volume which is going to the evaporation process, wherein we are trying to recover the brine or the salt which could be used for the manufacturing processes. Overall, this is what we call as a circular economy. It is giving back to the user or to the manufacturer what he is using in the manufacturing process. I move to the next slide. As we all know, in the past, there used to be an abundance of freshwater resources available to humanity and to the industrial consumers, whether it was with respect to the groundwaters, with respect to the surface waters or river waters, or now with respect to the sea waters. However, as we have grown and as we have seen historically, these freshwater resources are becoming scarce day by day. On the other hand, we have our municipal corporations, our common effluent treatment plant systems, wherein they have fixed capacities. They take in the waste water or they take in the effluent which the industry produces and try to treat that effluent. However, this capacity is fixed. With the growing trend of industrialization, with the growing resources, especially when it comes to the manufacturing, there is a lot of burden on the industrial customer from both the ends. On one end, his raw water resource is getting scarce, and on the other hand, he cannot discharge a particular volume of water to any kind of common effluent treatment plants or municipal corporations because the infrastructure is pretty much limited or constrained. Hence, there is a very tight sort of burden on the industrial customer in order to look at both the equilibrium, whether it is taking in the freshwater resource or discharging the water outside his premises. And that's where the concept of recovery of water, which is primarily used in their manufacturing process, in their production process, or for that matter, in any kind of applications which the industry is engaged with. Move to the next slide. This is a very interesting slide, and professionals who are engaged in the water treatment applications over the period of time would be able to correlate with this particular graph, which is on the left side, pretty nicely. It says that when you have a groundwater, the total dissolved solids, which is displayed on the x-axis, is pretty lenient, is pretty thin, is pretty small. Also on the y-axis, what we call as chemical oxygen demand, or COD, is also very less. So the groundwater treatment is definitely very, very simple. It does not require a complicated or a sophisticated treatment. As we move on the graph, we see from groundwater, we move towards the surface water. Surface water, for example, it's like a river water or a dam water or a canal water. Again, over here, the amount of salt composition or the salt concentration of surface water is pretty thin, is pretty lenient. And same is the case with fouling potential ingredients like BOD or COD. However, with the growing scarcity of groundwater and surface water, the impact of wastewater reuse is gaining momentum day by day. However, when we talk about wastewater reuse, the total dissolved solids, the salt concentration increases further, and also the amount of impurities on one hand, which we call as foulants, also increase. And there obviously is a question that if you further try and maximize the water recovery, these impurities are going to grow. And that's correct. When we talk about maximizing water recovery, especially the water which is being consumed by the industry in their manufacturing process, it gets concentrated. Hence, whether it is the salt concentration or whether it is the concentration of the organic or foulants is further going to enhance. And hence it becomes tougher to implement or have either minimal liquid discharge or zero liquid discharge. What we call as ZLD, which is zero liquid discharge, or MLD, which is minimal liquid discharge. When we speak to our customers and when the customers tell or express their needs, there are top two needs which are being segmented. When we talk about ZLD, the customer says that Is it possible to reduce the cost of evaporation? When we say evaporation, it is the process of thermal evaporation. Any kind of a thermal process, as we know, has a capital sort of investment, which is very high, which is very substantial. It also involves operational expenses, which are quite substantial. And as we progress in this presentation, we bring you some of the experiences which the industries have shared with us. Another concern for the zero liquid discharge customers is that what do we do with these salts? What do we do with the solid part which has been generated? Is there some mechanism whether we can reduce that waste or whether we can recover that waste? When we talk about MLD, the important question which the customers express is the reliability of maximizing the water recovery, because water recovery is something which is of prime concern to the customer over here. Reliability is also very important. Consistency in operation is definitely an important criteria. We move to the next slide. In the past, if we have seen some of the customers who would have preferred to go with the minimal liquid discharge or zero liquid discharge kind of applications, we would have seen that if the customer is primarily targeting water reuse kind of facility, which has been shown in yellow color over here, and it has been termed as a recovery which is up to 75%. So when we say recovery, it is the amount of water which is able to be recovered from the available wastewater, and the balanced water is either been fit to discharge or it has been put directly to the thermal processes. It could be the mechanical recompression or the MVR, or it could be the MEEs, which are the evaporators. So the process was that you recover up to say 60 to 70% of the wastewater, and the balance 30 to 35% was been put to the evaporation process or the thermal processes. However, as we understand that the thermal process is very capital intensive, and that's where we understood that if we offer the technology of reverse osmosis primarily to our customers, wherein they could extract or recover further water, which is say from 60 or 75% to almost up to 95%, wouldn't that be a sort of a practical solution where we can reduce the zero liquid discharge cost? Because ultimately what the customers will be looking at is the overall cost, which has been applied, whether it is for zero liquid discharge or whether it's for minimal liquid discharge. And when we compare the cost which is involved as a comparative between ZLD and MLD, we can see that if the customers are able to employ reverse osmosis based solutions and are able to extract further water or recover more water, the ZLD graph could be brought down and the total cost could be reduced up to 60%. And over here, the audience might wonder that, look at the x-axis. The x-axis shows that the salinity in the water grows. So as a water professional, we know that when we try and sort of maximize the water recovery, the concentrations of the water or the ionic impurities of the water grow, what we call as salinities. So as the salinity grows, it becomes tougher and tougher for the technologies to handle those. But DuPont is very proud that they have brought in conventional spiral wound membranes which can sustain that and can further maximize the recovery. I move to the next chart. This is a very interesting slide because, as we know, historically, there were very few places where actually minimal liquid discharge was been implemented. And as I shared, that primarily the usage was, or the method was, that we try and recover as much water as possible, which is say around 60% to 70%, and the balance has been treated with thermal processes. Most of the customers do ask us that, isn't that cumbersome that, if we are using an RO system, it makes sometimes complications. We are using different technologies for trying to treat the wastewater or trying to maximize the water recovery. And over here, if you look at the bottom end, we have gained some kind of impressions from our customers. When we interact with our customers, they do share what is the cost involved if they're going to go with a completely evaporation process, or if there is a process which can combine that with the RO processes. So on table number 1, what you have is the estimated capital cost on trying to treat a cubic meter of water on a daily basis. And on the second column, what you see is the estimated energy cost, or which is called as the power consumption, the energy consumption in terms of kilowatt hour per cubic meter of the feed. When you try and look at these numbers, those are pretty astonishing, because when we talk about having a complete evaporation process, and if you try and sort of implement stage-wise reverse osmosis solution, which has been put up over here, like RO1 is a low pressure, or a stage 1 reverse osmosis system, which is primarily brackish in nature. RO2 is a high pressure process, which is in normal terms called as a seawater process. And RO3, which is the ultra high pressure, or which is called as beyond the osmotic pressure of seawater. And if you compare the capital cost over here, those are very, very small as compared to total evaporation costs. On the second column, if you look at the energy cost, the energy if you spend on the evaporation process is pretty substantial, or I should say it's pretty huge. Again, power is something which we should be wary of. As we talk about water consumption, we should talk about power consumption as well. Energy is also becoming scarce. If you compare those with the stage 1, stage 2, and stage 3 reverse osmosis processes, and even if you total that up, it still is very, very small as compared to an evaporation process. Hence, when we talk about implementation of MLD or ZLD solution, definitely we understand that it calls for a combination of technologies. We aren't saying that RO is a complete solution. We are saying is that how we can help the customer to optimize the cost, to optimize his routine, wherein he would recover maximum water, he would make the water fit for reuse, and also try and meet the regulations, whether it is implemented by the government or it is being implemented by the industry themselves, wherein the technologies could be used to minimal the capex or the opex. We move towards the next slide. As in the earlier slide, we have seen the benefit of including RO as an important technology in a ZLD process. Apart from reducing the water which is going to the evaporation process, recovering maximum water with the conventional technology, because reverse osmosis membranes or handling reverse osmosis systems is pretty much now hands-on with several customers. Apart from that, there is also a spiral wound technology which is called as an ion separation technology, or conventionally it is called as a nanofiltration technology, which has been used to primarily separate the monovalent ions and the divalent ions. So taking the clue from textile wastewaters, in their dyeing process, they use sodium chloride as a dyeing salt or sodium sulfate as a dyeing salt. And definitely when they have the effluent which is coming out after the manufacturing process, these salts are present in the effluent. Apart from recovering the wastewater or trying to maximize the recovery of wastewater, Dupont also thought that why not have a solution where we could recover the salts, which can reduce the burden on the evaporation process and also can help the manufacturer to get the brine solution or to get the salt back for the dyeing process. Hence, a membrane technology which can do the separation of salts is also been quite popular in the recent time, and that's where we are coming to the point of circular economy. So when it comes to the membrane technology, I think the membrane technology can help the customers to a large extent in not only primarily trying to recover the wastewater, but also try and recover the salt which they can consume back in their manufacturing process. Move towards the next slide. This is a very interesting slide, and as water professionals, I think we understand this particular terminology of recovery, the concentrate, TDS, osmotic pressure. So in this particular slide, we have two graphs, one on the left side, one on the right side. The one on the left side takes an example of having a feed water salinity which is around 2000 milligrams per liter or 2000 parts per million. The x-axis is the point of recovery or the percentage of recovery, and on the y-axis we have termed that as concentrate or what is called as a reject solution. So as an example, if you have a feed salinity level of around 2000 ppm, and if you're able to recover a water which is around 75%, it means that the concentration is 4 times, which means that the concentrate TDS is around 8000 ppm. This gives you an indication that as you maximize the water recovery, the reject concentration grows. So when you move up the needle from say 80% to 90% to anything which is beyond that, what you end up is with a high salinity on the reject side. This is definitely a challenge. If you look at the graph on the right side, it talks about now the salinity level or the concentration on the x-axis and the osmotic pressure or the requirement of the driving force to treat that water on the y-axis, which is called as the osmotic pressure, which is noted in terms of say PSI, the nomenclature for pressure. And as the total dissolved solids or the concentration on the x-axis grow, we understand that the osmotic pressure requirement also will grow, which means that we, on one hand, when we're trying to maximize the recovery, the amount of concentration on the reject side grows, the TDS grows, and once the TDS starts growing, the requirement of the driving pressure or the osmotic pressure also grows. And this gave us an input as to what is the kind of innovation which a technology partner can bring in. We move towards the next slide. We looked at water recovery. We looked at salt composition or salt concentration. Now let's look at the other parameter which is also very critical when it comes to challenging waters, which is called as COD, chemical oxygen demand. And especially when we talk about wastewaters, the concentration of COD is pretty substantial. Even though there are technologies which have been used in the pre-treatment which could reduce the COD, still at the inlet of the RO element, we find the concentration and presence of COD. Over here, there are two different charts, and the two different charts denote two different values of inlet COD to the RO elements. For example, on the left side, we have tagged it as 60 ppm, 60 ppm of COD. And as we said, that as we maximize the recovery, if you reach a point of 90% of recovery, the point of concentration of COD moves from 60 to almost COD to almost 600, which is 10 times because we are trying to increase the recovery by 90%. Imagine that instead of 60 ppm of COD, the value of COD is now around 150 at the inlet of RO element. And look at the point where if you're trying to extract 90% recovery, the value of COD jumps to almost 1500 ppm. We all are aware that as this value grows, the challenges of sustaining the recovery of water, the challenge of resistance to fouling also increase on the RO elements. This is again an avenue which we thought has to be taken as a point of consideration if we are in the zone where we want to move towards minimal liquid discharge or zero liquid discharge. Move towards the next slide. So we talked about salt concentration, we talked about COD. Now, from the user perspective, let's talk about the salt, which he uses in the manufacturing process. Imagine the amount of salt waste which is being created if the user is being forced to implement zero liquid discharge. Over here again, there are two charts, one on the left side, one on the right side. Look at the amount of salt which needs to be disposed of. The assumption is that we take a volume of water which is around 1000 cubic meters per hour. We are trying to treat a water which is having 2000 milligrams per liter of total dissolved solids, and we are assuming that the volume of salt which needs to be disposed is around 36,000. If you look, the amount of trucks which are required to dispose of the salts are around 1.25, which is like 1 plus 1 and 1/4. This salt primarily has been taken to the landfill, or it's been pretty much disposed of. Imagine if the salt concentration increases from 2000 ppm to 5000 ppm, considering the same volume of water which needs to be treated, the amount of trucks which are required to basically take off or dispose this salt. Primarily, the disposal of salt mechanism currently which is implemented generally by most of the applications is with respect to the landfill. And definitely this is not sustainable. So as a technology provider, are there solutions where we could reduce the amount of salt which is being allowed to go as a landfill? Is there a technology which is available to primarily recover or increase the brine concentration so that this salt could be put back to the use by the manufacturer? And that's where that shows or throws another avenue for the technology provider. So we have looked at three important avenues. One is the total dissolved salts, one is the amount of COD, which is a foulant, and thirdly, the impact of salt on implementing a zero liquid discharge process. Move towards the next slide. The next slide primarily talks about the kind of portfolio what Dupont brings in. As we said that implementing a minimal liquid discharge or a zero liquid discharge is a composition of various technologies, is a combination of various technologies, whether it could be spiral wound reverse osmosis or nanofiltration membranes. It could be a use of ion exchange resins, which is primarily used for softening or COD reduction, which is like an organic scavenging process. Ultrafiltration processes, which are hollow fiber UF membranes, which could be used to reduce the particulate matter, to eliminate the suspended impurities which could have an impact on the downstream equipments. It could be the membrane bioreactors, which could aid the biological process. It could be the MABR, which is the membrane aerated biofilm reactors, which further enhances the oxygen transfer and helps the biological systems. It could be the closed circuit RO systems where we try and sort of maximize the recovery and reduce the waste by implementing processes which will reduce the volume which is being wasted. We move towards the next slide, which talks about these various technologies in a little bit detail. This particular slide talks about the various applications of the technology. As we all understand that trying to solve a particular challenge or trying to meet a customer need is not something which a single technology can do. Every technology will have its own kind of advantages and will have its own kind of shortcomings which have to be overcome. Hence, Dupont Water Solutions brings all these technologies in front of the customer and trying to sort of suggest what could be the optimized solution when a customer tries to think about treating the wastewaters, treating any kind of challenging waters. It could be RO systems, wherein we try and sort of use desalination processes, maximize the recovery. It could be ion exchange resin process, wherein Dupont has been a market leader and a technology leader. It could be ultrafiltration processes, which is the hollow fiber UF membranes available now in two different chemistries. It could be polyether sulfone based chemistry. It could be a PVDF chemistry. These are pressurized UF systems. There is also a possibility of suggesting submerged UF system. When we talk about CCRO, it is the closed circuit reverse osmosis system, wherein we have significant improvements in the recovery. It also helps in reducing the energy. It also helps in saving the footprint of a customer, wherein instead of going with stage-wise system of RO processes, we could have compact reverse osmosis systems trying to maximize the recovery. We could have MBR, which is the membrane bioreactor, which has been coupled along with the biological system and simplifies the overall system and also makes the system cost pretty optimized. And MBR can also eliminate the secondary clarifier or the tertiary filters and can put water directly into the RO system. MABR is something very interesting which is coming up and it is just catching the attention. These are again hollow fiber membranes which are being actually immersed into the biological systems. This process is very OPEX saving intensive, wherein we reduce the energy consumption as compared to the normal bubble type diffuser processes. There is a significant energy saving. There is a significant footprint saving as well, especially when we talk about implementing biological systems for metropolitan cities like Mumbai, Delhi, Chennai, Bangalore, or Calcutta. The footprint savings are pretty huge. And this is another technology which Dupont brings to the forefront of the customer. Move towards the next slide. The slide talks about the typical process which has been employed in a minimal liquid discharge system or a zero liquid discharge system, where we have the primary process, the secondary process, and the tertiary process. And over here, you will see those technologies been implemented in a way which aids each other. So it could have a UF system which could aid the RO process by providing a very low turbidity or a very low suspended solids load on the RO membrane. With the help of stage 1 RO process, stage 2 and stage 3, we are able to maximize the recovery. We can have an ion separation process or a nanofiltration technology which can further enhance the water recovery, which can also provide salt recovery to the customer. And obviously, there is a position of evaporation process or downstream crystallizer wherein the customer can achieve the ultimate aim of zero liquid discharge. We go in a little bit of detail in the subsequent slide. As we know that there could be various kinds of pathways, which could be implemented by the customer depending on the economic situation. So in this particular slide, you will see there is pathway A, which has been put up in the yellow dot, pathway B, path C, and path D. Path A has been pretty conventional, where you treat the water and make the water fit for discharge or reuse. And over there, you can see the concentration which has been put in terms of total dissolved solids, which is around 6 to 8%. When we say 6%, it's around 60,000 milligrams per liter. There could be a pathway B wherein this particular water, which is around 6 to 8%, is been put to the thermal processes of evaporation or crystallization. However, with the innovative technologies coming in globally, there could be a path C wherein, with the help of conventional spiral wound technology, we could further recover the water and reduce the volume which is going to the evaporation process, wherein the concentration can rise up to almost 10%. 10% is almost 1 lakh milligrams per liter. It could be a path D as well, wherein we recover the salt. Over there, it has been shown as 6 to 8% of purified sodium chloride. Hence, depending on the need of the customer, depending on the cost benefit analysis, there could be several paths. And this is what we see currently, which is being utilized by most of the industrial users. When we say about the industrialized use, we are also talking about the municipal use, because municipal is something which has also been very encouraging in India. The municipal wastewater use is gaining momentum, and we are talking about not only treating the water which is fit to be reused, but we are also trying to see that how we can further put the water back and give it back to the industries. Hence, based on this particular philosophy, there could be different pathways which the industry can use. We move towards the next slide. As we have seen the challenges when it comes to wastewaters or challenging waters, the amount of total dissolved solid grows, the amount of foulant grow, the amount of impurities which needs to be treated with the spiral wound membranes grow. That definitely is an avenue where the technology provider like Dupont can give you technologies which not only can sustain this, but actually can enhance your overall wastewater treatment processes. So when you look at the right side of your slide, you will see over there that when it comes to the tertiary treatment, where we have the conventional ultrafiltration system, which is followed by the ion exchange resin-based system in order to remove the scale potential agents like calcium salts, what follows is basically stages of RO system. Stage 1, which is primarily brackish water, stage 2, which is primarily seawater, and stage 3, it could be a combination of seawater or it could be an ultra high pressure reverse osmosis system. There comes a sort of innovation wherein DuPont has developed 40 Life series of products, where these 40 Life series of product offer several benefits. On one hand, we know the challenge that when a customer talks to us about maximizing the recovery, the most important fact to remember is not only reliability or sustainability, but are the membranes more fouling resistance in nature? Are the membranes capable enough to handle the foulants in a better manner? Are the membranes able to provide a longer duration? Are the membranes taking higher energy? These are some important facts which needs to be taken into consideration. As I said, when new technologies are being brought in, and every technology finds its own kind of spot wherein it could be an advantage in certain section, or it could be a disadvantage or a weakness in certain section. However, as we have sort of surveyed most of the industrial users, some of the needs of the users have been captured, and these needs have been transferred or translated into the product features which have been listed over here. Some of the benefits which the customer derive, whether it is with respect to energy saving, whether it is with respect to the reduction of cleaning. Another important factor which the industrial user takes into consideration is the uptime or the manufacturing time or the productivity which the membranes have to deliver. If the membranes are not able to deliver higher productivity time, sometimes technology doesn't find its place. Hence, it becomes very, very crucial for a technology provider. And that's where Dupont Water Solutions comes into the foreplay with the partnership of the customers. At the end of the day, when the solutions are brought in, it should help the customer, isn't it? So looking at whatever the needs of the customer are and looking at how we can convert those needs into the products which the customers can have it and can help is something which Dupont has been continuously working on. And this has been possible only with the continuous engagement with the customers. And we also feel that this is a platform where we can get continuously engaged, if not on face-to-face basis, but having a virtual kind of an engagement, does help us. So whether it is with respect to the various solutions, this is something which we try and sort of implement and help the customers to achieve the goal of minimal liquid discharge or zero liquid discharge. We move towards the next slide. As we said in the beginning, that we need to have some practical cases, we need to have some practical examples wherein these technologies have been put to use. Technologies which can help deliver circular economy have been put to use. And especially when you talk to textile industries have been pretty much water intensive. Those industries have also been pushed by government regulations in order to implement zero liquid discharge. So whenever there is an engagement with a textile customer, there are a lot of challenges which the textile customers do express. And there's the point where we help them try and sort of achieve the goals, not only from the specific aims of the industry, but also from the point of view of sustainability, where we could maximize the water recovery, give less water to the evaporation process, try and recover salts wherein it could be used for the manufacturing process. Move towards the next slide over here. This slide sort of displays, the water samples, and this is a real story. When we try and take the water samples from the various stages of the primary process, the secondary process, after the RO, if there is an RO reject, if we have a sort of a treatment process of ion separation or nanofiltration, what's the kind of treated water sample what we get. And there's the place where we're trying to sort of conserve the natural resources which are available, whether it is producing or maximizing the water which has been sort of been allowed to discharge or which has been allowed to go waste. We're trying to bring back the salt which can be used for manufacturing process. And definitely there is an aim that we conserve energy, we spend less energy. The technologies definitely have to take this viewpoint that when it comes to applications, the energy consumptions are being pretty kept at an optimized level in order to deliver the output. These are some of the examples which we have taken from the industry. And we have the last couple of slides coming up actually, which talks about some numbers over here. And as we said before, that implementing a minimal liquid discharge vis-a-vis implementing a zero liquid discharge, primarily talking about only a wastewater reuse facility, can reduce the overall cost by 60%. And here is a sort of a live example where we have taken an application where we are trying to maximize the recovery up to almost 95%. And instead of putting a large volume of water to the thermal processes or putting the volume directly without minimal liquid discharge into the zero liquid discharge processes, what are the savings which the customer get? The slide takes a specific example of feed TDS, which is around 8,000 milligrams per liter, producing salt, which is around 8 kilograms. And we have taken the cost of NaCl or sodium chloride, which is available in the Indian market over here. So if you're able to maximize the water recovery from a point of 70% to 95%, what is the water saving which is available that has been translated in terms of monetary value? That is the amount of water which is available as a recycled water to the user. If you're able to generate purified brine stream, that's an additional value which has been created for the customer. So overall, if you put these two buckets together, which is the recycled water, which is available as a fresh water for manufacturing process, plus the purified brine solution, if it has been recovered, you can see it adds up to almost like more than $1 per cubic meter. And there's where if you combine the pre-treatment costs and the RO system cost, you will see a substantial saving if we are combining the processes of minimal liquid discharge along with zero liquid discharge rather than implementing only zero liquid discharge. We move towards the penultimate slide, which again sort of buckets these three different philosophies together. So we have three buckets over here. One is the water which has been fit to discharge or is allowed to discharge. The second bucket, which is shown in the middle over here, is implementing a technology which is complementing ZLD or helping ZLD, which is a combination of minimal liquid discharge and zero liquid discharge. And last is purely implementing thermal processes and zero liquid discharge. So as we have seen in the earlier slide, if you're allowing the water to be fit for discharge, the cost is around $0.6 per meter cube. When we're trying to use MLD solution, the amount of savings what has been done, if you deduct those savings, the treatment cost is around $0.7 per meter cube. And if you reduce the savings in the thermal processes, the overall cost per meter cube is around $2.4 per cubic meters. So if you look at these numbers, it's very interesting. There always throws these kinds of avenues where rather than allowing the water to be discharged after doing the primary treatment or the secondary treatment, we should definitely look at technologies wherein we could help recover the water to a large extent with a minimal OPEX, which is the difference of only $0.1 per cubic meter. And these savings could be further enhanced by using technologies which are definitely helping the customers when we talk about 40 life series of RO and NF elements. We move towards the last slide, which the customers can get benefit out of it, is been trying to see that how they could use or try and see the prediction of using these technologies in their kind of atmosphere. So as a Dupont representative, we are always available. We are always there to help the customer. But if the customer wants to try themselves and try and see that how these technologies can work together and help them to run a sort of simulation, there is a Wave, which is a design software program which is available on the Dupont website. This is a multi-product design software where we can have the UF systems, where you can design the RO systems, where you can use the ion exchange based resins, and try and see that what is the kind of performance which these membranes can reach up to. As I said,
Excuse me,
as a
Mahesh.
representative from Dupont, we are always available, but this is something which the customers can use. With this, I end my presentation.
Thank you so much, Mahesh. It was a wonderful presentation, and I'm sure you highlighted some of the key areas and key topics related to the covered given topic. And now we open it for the question answer session. Also, we have shared a small questionnaire at the poll section too. So maybe if you have to say something about that questionnaire too, it's all yours. You can definitely say something about the poll which we have shared, the questionnaire which we wanted
Yeah,
participants to see and answer. Anything from your side?
yeah. Thanks, ma'am. Yeah, I can see some of the questions which have come up, and I think we have some time basically to answer those questions. We try and sort of address the primary questions, but to our audience we'll definitely try and come back to you if because of the scarcity of time we are unable to answer some of the other questions. Yes, so um, there are questions which are coming up where how the membranes can help reduce the fouling or primarily avoid the fouling. So yes, these are very important questions, and as we have seen in the presentation, and as we experience in the practical industrial nomenclature, that normally when it is a wastewater it will have a high fouling potential, and these kinds of foulants are definitely going to impact the performance of the RO system. Hence, DuPont as a technology partner has been progressing in that direction, whether it is the change in the surface chemistry of the reverse osmosis membranes, or it's a change in the kind of feed spacer which has been sort of impregnated in the RO membranes, or it is with trying to see that how the structure of the element is been designed. All these features, whether it is with respect to the membranes per se, or it is the mechanical design per se, DuPont has always been in the forefront to help the customers in order to see that how foulants like biofouling, organic fouling are being kept to the minimum. And that's where the birth of Fortilise CR100, which was being introduced into the market, which is coming up with an extremely lower differential pressure, has been helped the customer. We're also getting questions about the ultra high pressure RO. I think the ultra high pressure RO is something which is very uniquely offered by DuPont. The ultra high pressure RO is an element which can go up to a pressure of 120 bar, which means that the conventional reverse osmosis membranes, or for that matter the seawater reverse osmosis membranes, had a threshold of 80 bar. However, UHP RO is pushing that threshold from 80 bar to 120 bar, which means that we can further enhance or maximize the water recovery using the conventional spiral wound technology. As we answer some of the questions, we are getting some more questions related to our ion separation membranes, which is the NF membranes. Yes, the ion separation membranes can definitely aid the aim or the purpose of minimal liquid discharge and zero liquid discharge, and can help basically separation of monovalent ions and divalent ions, and can further help the customer as we talk about circular economy to not only maximize the water recovery, putting less water to the evaporation process, but also putting the purified brine solution back to the customer. We have, I think, the last question which we can take up is with respect to the salt concentration. Yes, this is very interesting because as we shared in the presentation, salt concentration is something which is by chemistry, which is by nature, is definitely going to grow. And that's where we mentioned that it calls for a combination of technologies. Some of the technologies which are conventional will definitely find a place. For instance, I think one of our audience has asked a question about salt precipitation, or salt which will definitely have an impact when we talk about calcium hardness, when we talk about silica. And that's where we say to our customers that try and look out for optimization. there definitely could be a place wherein we could reduce the load of calcium hardness, or we can reduce the load of silica hardness by giving solutions which are conventional in nature, like the lime softening process or the chemical precipitation process. However, these processes have been consuming a lot of chemicals. These processes take a large footprint. These processes also deliver a large amount of sludge. Hence, this calls for an optimization. And that's where engagement with solution providers or OEM partners along with the end user actually is helping us. What we are saying is we should find a place for these processes in the complete chain of technology, in the complete chain of treatment process. It may happen that stage one may not require a treatment philosophy of hardness reduction. It may happen that the stage one can sustain the concentration of salts on the reject side. It might happen that the hardness removal process can be done in between stage one and stage two, or in between stage two and stage three, again depending on the combination and concentration of salts. Apart from the conventional technologies, there are technologies which are coming to forefront, like the ion exchange based resin technology, which can be used. We also see a lot of sort of acceptance and adoption of ion exchange resins which are being combined with RO processes. On the other hand, we also have the CCRO, or the desalinated systems, which can sustain the hardness to a particular threshold before the brine has been discharged. So definitely it calls for further optimization. As we have shared during our presentation, a zero liquid discharge is definitely a challenge to any solution provider, is a challenge to any OEM partner, and that's where constant engagement, continuous engagement, and trying to see how the overall system capex and the system opex could be optimized is the field where, as professionals, we'll definitely have to work into.
So I think that was the last question for today, though we're really receiving a lot of queries further, which we will be answering through email. So from our side, we would like to thank, first of all, Mahesh. It was wonderful presentation, and the way you took it forward, it was really nice. And thank you so much for your time and a wonderful presentation, of course. For the participants, it's lovely to see so many in numbers, and I hope you found this overall program enriching. We keep doing such programs time to time, and we look forward to your participation further. We will be doing more such series, we'll be doing more such events, and to follow and to understand what is the next coming up, please follow us on our various social handles: Twitter, LinkedIn, and Facebook. And you can also write to us at info@thewaterdigest.com. And thank you so much for joining us today. Thank you so much, Mahesh.
Thank you, everybody. Thank you for attending, and thank you for taking out your invaluable time. It was very nice interacting. Thank you, Water Digest, and thank you, everybody.